Hello and welcome again to my Physics Online video lecture series. Today's video I'm going to be doing a short introduction to collisions between extended bodies. This is really meant to be more of a what are the principles involved. It would require a different set of videos to really work any examples for these because the examples tend to be longer than is conducive to put at the end of a simple 15-ish minute video. So I'm just going to be walking through the basic principles, and hopefully I'll have time to make a couple example videos to go with this later. This is a continuation of our discussion of rotational dynamics. We have already kind of in some sense discussed the principles that are going to be involved. So you may recall from previous videos that if you want to change the energy of a system, you apply work, and in like manner, force changes linear momentum. So if you want to change the linear momentum of a system or of an object, you must apply a force to that object from outside, and torque is what you do if you want to change the angular momentum. So applying a net torque to an object changes the object's angular momentum. And what this set of principles implies is that for a closed system, interactions within that closed system will tend to conserve mechanical energy, linear momentum, and angular momentum. And so in order to change one or more of these, there must be something from outside the system interacting with the system to apply either work, force, or torque. Now with that said, of these, this top one actually is changeable within the system because when you have a collision, you can have sound from the collision, you can have damage. That basically means, for example, like if you have two cars crash into each other and you bend up the bumper of one of the cars, that also took some amount of work, and that essentially steals some of the mechanical energy from the system. So these things mean that energy may not be conserved. So a collision may not actually be elastic. So a collision can be elastic or not, depending on the circumstances. These two, however, for a macroscopic collision, you have to be able to identify an outside object to apply a force or torque if you want them to change linear momentum or change angular momentum during a collision. Okay, so the basic idea is that when you're looking at a collision between extended bodies, angular momentum will tend to be conserved. But you're going to have to identify the axis about which it's being conserved. So angular momentum is conserved, but identify axis of rotation. And there could be some torque, but usually there's not some object to apply a torque. So this is unless outside torque is applied. But again, you'd have to find something that could supply that outside torque. So generally speaking, you're identifying the axis of rotation, and then you're basically doing sum of the initial values, so sum of the initial angular momentums and sum of the final angular momentums has to be equal. Second principle is linear momentum should be conserved. And this is assuming that there's not some external force. So linear momentum is conserved unless there's an outside force. And an outside torque does imply an outside force as well, But it's possible, for example, that you might have all of your outside forces balanced, but not all of your torques balanced because of the torque being an R cross F. But one example of an outside force where there's no torque about some axis of rotation would be like if you have a stick that's free to rotate about a peg. So maybe you drilled like a hole in this thing and there's like a peg inside of this hole, and now you have a collision with this, like so. This can rotate freely, but it can't translate freely, and this peg right here applies force. So it can apply a force in some direction. I'm showing it as if it's down, but it could be an upward force or whatever, to prevent this from sliding. And so everything can rotate, but not necessarily slide. Now there exists a point at which this can hit the stick, and no force is needed by this peg when this recoils and this recoils for momentum to be conserved. That's kind of like not exactly the sweet spot on like a baseball bat or tennis racket, but it's the spot at which you get the least recoil when you're hitting the ball. And so it's sort of like if you don't want to develop tennis shoulder or whatever sports injuries, that's the part that you'd want to hit the ball with your racket or bat or whatever, where this peg is really now representing your hands on the handle of the bat. So that's kind of like the linear momentum conservation idea. And again, what we'd do is say sum of the linear momentum initially and sum of the linear momentum finally must be equal. The last part is the energy considerations. And these energy considerations, largely it's in a problem you would be told this is an elastic collision, or this is not an elastic collision but the objects stick together, or this fraction of the energy is lost. Or maybe you would solve for these two things and then use those to figure out how much energy might be lost in the system, etc. So basic tips and tricks. As with point-object collisions in linear momentum, there's several types of collisions that we like to model. The first of these is the elastic collision. In that collision, the two objects will collide. They will likely bounce off of each other in some sense, and energy, momentum, and angular momentum should all be conserved. You end up with an extra equation that says sum of kinetic energies initial and sum of kinetic energies final are equal. Typically, there could also be some potential energy. Second type that we generally like to have is totally inelastic. So perfectly or totally inelastic. And that means the two objects stick together. For this collision type, you have some former version of center of mass velocities being equal after the collision, and also rotational rates being equal after the collision. But interpreting what these two things mean may take some doing. For example, if I have a stick like this, and maybe I happen to collide with it and stick together with a disc on the stick, there could be some rotation of the system, and these two things are rotating together. There's also going to be some sort of a center of mass velocity for both of them after the collision. So they're sort of like moving together this way, but as they do it, they're kind of like rotating about. So they're kind of like spinning along like this. Or from the side, they'd be spinning along like this as they slide across the surface. To figure out this one, generally speaking, you have some axis of rotation which might be about the center of mass of the system, for example. And so maybe the system happens to rotate together about this point, for these two being roughly equal masses. And so essentially you would have this right here being your R for the stick, and this one right here being your R for the disk for the purpose of angular momentum. And so what you'd be able to find is that for this being my axis of rotation, I initially had some velocity of just the disk maybe, and 0 for this, and afterwards I have velocity of the disk in an omega sense, and I have an omega for the stick, and so the two kind of like move together to conserve that angular momentum. And then I also have, if they have the same mass, maybe like half as much velocity translation-wise as I had before. And you could go figure out how much energy is lost if these conditions are met. The third type is that one of the objects is fixed in place. So object fixed in place, but free to rotate. So that one kind of devolves back to something like this, where I've got a peg through the stick and it can't slide, but it can rotate about that peg. And that forces the axis of rotation to be wherever it's fixed at. These two conditions may be satisfied, but this one may suddenly not be satisfied because there could be an outside force. So this condition has to be satisfied. This one probably won't be. This one probably won't be. For our conceptual examples in this video, I think what I'll do is just kind of ask what kind of collision do we have for one or two types of collision. So our first one is you have a baseball outfielder making a leaping catch. So they've like jumped up into the air and their hands way up and they catch the baseball in the glove. What kind of collision would that be if we looked at these classifications of collision types? So is that elastic? Is it perfectly inelastic objects sticking together? Or is it a collision with an object fixed in place but free to rotate? Or is it some other kind? So lacking any of these three obvious simplifications. Well, the fact that the catcher caught the baseball means that the outfielder caught the baseball means that the two are basically in some sense like stuck together. So this one would fit under the second type of collisions that I listed up there. Second kind of collision. Same game, we're playing baseball still. The batter takes a swing at the baseball and hits it with his bat, and the catcher and umpire and whoever else is nearby hears a very loud thwack, like loud sound when they hit. Okay, so what kind of collision is this? Well, it's not really going to be an elastic collision because you hear that loud sound. You've taken some mechanical energy from the system. The two objects aren't going to stick together because the ball obviously has now been hit to the outfielder who made the leaping catch. But you can look at the collision between the bat and the ball. The bat, in some sense, has a fixed end that is not allowing it to recoil so much. Yeah, there may be some recoil, but for the most part it continues its motion, albeit maybe a little bit more slowly. So we have a sort of type 3 collision here. Okay. So the point of these two sort of conceptual examples that I've given for you is this. So this one was essentially like type 2. This one is type 3. The point here was not to like put numbers to the screen or numbers to paper or what have you and write out an example. The point was, can we take a sort of like story problem and identify which of these three approaches we might use, and therefore what set of conservation laws we might make use of to solve the problem. Alright, that's all that I'm going to do in this video. I do intend eventually to release some more videos with specific examples, although it may be some time before I get to those. But that's all for today's video. Thanks for watching. hopefully you've learned something from it, and or hopefully it's helped clarify this topic for you.